The work that I'm going to talk to you about today is certainly not going to encompass everything that I've done over the last many number of years, but I'm going to tell you some highlights of some of the recent things that we've been working on. The stuff that I will talk about has been done, all the work essentially has been done by other people. I'm just a proxy to come and talk about what it is that they've done. The graduate students and the postdocs that did the work are listed here, and Lauren Pfeiffer and Ken West, of course, are senior scientists now working at Princeton University, who supplied the samples. I thought it would be nice if I talked about results both from single-layer two-dimensional electron systems, which was pretty much all we talked about in 1985, and also more recently we've begun to learn a lot about double-layer two-dimensional electron gases, and I'll tell you about those. That's what I have focused a great deal of my attention in the last really 20 years on double-layer systems. Very excited about them. So I'll begin by telling you about the single-layer case. And again, I'm going to focus only on a very narrow fragment of all the physics that you can do here. It's obviously going to be quantum Hall physics. And this picture is a very old one now. It's almost, 25 or 30 years old, showing fractional quantum Hall states in the lowest Landau level, many of them. This was a good sample for that in that era, 1988 or so. But what I'm going to focus on is not the fractional quantized Hall effect in the lowest Landau level, but in fact what goes on in terms of collective behavior in the first excited Landau level. So you can imagine a diagram sort of like this, which for reasons only known to computers, the spin sublevels of this Landau level, or there's only one of them here, there's both of them here, there's only one. I have no idea why that is. It's not true in the actual view graph. But anyway, I'm going to talk about life in the first excited Landau level, and I hope that a good fraction of what I have to show you actually appears on the view graphs. That would be nice. So this is an old picture going back 1987 in which the discovery was first made of a fractional quantized Hall effect in the first excited Landau level. So this is ancient data, very old. It was taken by Bob Willett, myself, and Horst Stormer, Dan Suey in the late 80s at Bell Laboratories. And you can see here that there's a very deep minimum in the longitudinal resistance at 5/2 filling. So this was very exciting because, of course, before that, the only fractional quantum Hall states we knew about in nature always had an even denominator an odd denominator. For example, 1/3 state, 2/5 state, 3/7, and so forth. So this was an anomaly and one that required an explanation, which I'm happy to say took years to develop. And in fact, it's not even clear that we completely understand the state now. So that's what I'm going to talk about, what goes on here at 5/2 filling. As time went on, of course, samples got better. Here's just a couple years later, 1989. Now the minimum is deeper. It's going down as the temperature is reduced, which is, good. There's a strong Hall plateau at 5/2 filling. So this was a much better sample. Something that we did not recognize at the time is that there were peculiar. Somebody did, actually. It was Klaus, who asked a question at the EP2DS in Grenoble. He pointed to these and said, what's going on there with the Hall resistance? It's going down and then up again. Similarly, it's going kind of up and down there. We didn't know what those things were at the time, and we mumbled various things that were incorrect about what it must be due to. But we've subsequently found out that those were real. And as, again, samples got better, this is quite a jump forward in time. In the 13 years, those non-monotonicities in the Hall resistance became extremely pronounced, and in fact, became quantized. The Hall resistance would quantize itself back to the nearest integer value. So here again is the 5/2 plateau, but adjacent to it are two more plateaus, one at an integer value and the other one also at an integer value. So these were really strange, something new. We now know at least a little bit about them. These are insulating configurations of the electron gas as opposed to the liquid-like states that you have in say, 5/2 filling. But we don't have a great deal of knowledge, I would say, about the internal structure of these insulators. They're presumably related to Wigner crystals in one way or another, maybe with more than one electron per unit cell, but really it's not well known what these things are. But they're undeniably there, as Klaus pointed out really long ago. So samples have still gotten better, and furthermore, so has the ability to cool samples down to low temperatures. I wish this were my data. It's not. It's Gabor Sathi's data from Purdue, with a sample, I believe, grown by Mike Manfra. But nonetheless, this is the same basic thing. Now we're at 7 millikelvin. There's the 5/2 plateau. No one would argue that that's a plateau. It's perfectly quantized. These integer quantum Hall we call them the reentrant states, are well developed. There's a 7/3 state. There's an 8/3 state. There's a, 3 minus 1/5. I guess 2 plus 1/5 is not so clear in this data. There's even a state at 2 plus 6/13, possibly. So this is sort of where the field is in terms of the best samples at the lowest temperatures, at least that I know about. It's very dramatic, and as you can tell, there's just lots of stuff going on. The electron gas in the n=1 Landau level has a hard time making its mind up whether it wants to be in a liquid state or wants to be in a solid state. Just exactly what the details are of the electronic configuration are very, very subtle, and there's lots to look at. Now, before this data, which is just a couple of years old, we already knew there was something fishy going on in the n=1 Landau level. Here again is data at 5/2 filling in a sample in which I'm about to rotate it. I'm going to rotate it in the magnetic field so that I can add an additional component of field in the plane. And there's two traces there, a red one and a blue one. They correspond to measuring with the current largely along one crystallographic axis, 110, which is one of the natural cleavage planes, or 11 baro, the two orthogonal natural directions in the sample. And as you can see, for these data, the two results are pretty much the same, and you would expect them to be the same. It's a two-dimensional electron gas, pretty much isotropic. You don't expect much difference. However, when you rotate the sample and put a parallel magnetic field on, something very clearly different happens. And the resistance in one direction, in this case it's the 110 direction, becomes extremely large at 5/2 filling, while at the same time the resistance in the 11 baro direction becomes small. So this tells you something is interesting going on, and that maybe there's a competition here between phases, some of which are stabilized when there's a parallel magnetic field on, some of which are stable when there is no parallel field, just depends. Now, that observation was not made in a vacuum. Of course, the theorists are always busy. Here's a paper from 2000, actually, by Ed Rezai and Duncan Haldane, where they're doing numerical calculations for 5/2 filling, trying to decide, well, can I see in the numerics the 5/2 incompressible states show up? And the answer is yes, but it's just barely there. And it's right on the edge, they found anyway, it's right on the edge of a phase transition to a different type of state, which has stripe-like order. In other words, some type of one-dimensional broken symmetry order. So that we knew that these kinds of things were possible, and so the data in some sense was not a tremendous surprise. Now, I'm not going in chronological order here, but here's another picture, which looks like it came out more or less correct. This is some data taken in our lab, actually in the late 90s, in which again you see the 5/2 filling, and red and blue again correspond to the current flowing in these two orthogonal directions, and pretty much 5/2 and 7/2 are what we would call isotropic. The resistance is pretty much the same when you measure in these two different directions. But if you go to 9/2, which is now in the n=2, or the third Landau level, it's very, very different in the two directions. In this case, in 11 baro, you get a tremendous resistance spike and a very deep minimum for the resistance measured along 110. This is not in a tilted field. This is just with the field perpendicular. These are very, very high mobility samples. This effect is only seen, as far as we can tell, with samples of mobility of order 10 million and above. So it took the best samples to find this thing. It's not particularly low temperature. This is 25 millikelvin. You can see the effect at 75 millikelvin. So there's something very clearly interesting going on, and it's obviously not a fractional quantum Hall effect. It's something else. So that really sets the stage for what I want to talk about. What I've sort of shown you is that the n=1 Landau level seems to sit at a boundary between two sorts of regimes. At high magnetic field in the lowest Landau level, all we have are fractional quantum Hall states. They're beautiful. We have lots and lots of them. There's no half filling. There's no stripe phases. It's fractional quantum Hall liquid physics. On the other hand, if we go into the n=1, so 2, 3, 4, and so forth, there are these anisotropic states, which we think are some type of charge density wave or nematic electron liquid crystal. Depends on what language you choose to use. Those, however, are not fractional quantum Hall states. In between is the n=1 Landau level, where we know there are fractional quantum Hall states. 5/2 is one of them. We now know there are several others, as I showed you actually in the data from Gabor Sathi and others. But we also know that if we tilt the thing, we can drive the system into an anisotropic state. And furthermore, even if we don't tilt it, there are these insulating phases. So basically everything that I've talked about occurs in the n=1 Landau level. It's a complicated place. There's a lot of states that are apparently close in energy and competing. So I want to talk to you about some newer results regarding that. So here's a picture. It's a little hard to see, and I apologize for that. But here's a typical sample, typically high mobility sample, about 16 million. This is the density. And there's the 5/2 fractional quantum Hall state. There's the 7/3 state, the 8/3, and so forth. More or less, it's anisotropic, and don't ask me about this. So it's more or less isotropic. At the same time, if we measure the Hall resistance, we see these reentrant integers developing. It's not so strong in this sample because it's low density, but there's a nice Hall plateau in there. The field is perpendicular for these data. If I tilt the magnetic field, I've already told you what's going to happen, at least for some of it. Around 5/2, the resistance becomes anisotropic, and the 5/2 state itself weakens. This is generically the case, that as you add parallel magnetic field, the liquid state at 5/2 filling seems to be destroyed. You can see also that the fractional quantum Hall states at 8/3 filling and 7/3 filling, which are the 1/3 and the 2/3 state of the n=1 Landau level, are still nice and robust. So this is not so surprising. It really follows from what I've already shown you. What didn't, well, let me back up here for a second. So I would say that a common interpretation without a tremendous amount of real justification, maybe we hear some more about that at the conference today, is that in this region where there's high anisotropy, we again have some type of stripe phase or pneumatic electronic liquid crystal. So let me go on then to show you what happens if you tilt the sample further. So now we're tilting the sample all the way out to 75 degrees. So we have to apply a much larger total magnetic field in order to have the same component perpendicular to produce 5/2 filling. But here we have, I don't see how much it is, but there's a lot of magnetic field, obviously, applied along in the plane, whereas there's still 2.6 Tesla or so applied perpendicular. Again, the 5/2 state is completely missing, but what's remarkable is over here in the resistivity. All that anisotropy that we had at 59 degrees of tilt is gone. It's gone. And now the system appears to be isotropic all over again, although not supporting any quantized Hall state at 5/2 filling. So the system seems to have gone from the liquid state at 5/2 to some type of stripe-like state at intermediate tilt angles, and then back to a compressible isotropic state when the parallel field is really large. So, and I won't bother talking about the temperature dependence. So there's some type of strange zoology here that you're able to access with this parallel magnetic field. And of course, I'm not telling you, don't really know how the parallel field drives these transitions, but apparently the system goes through a series of phases as you increase the parallel field. From what we know to be a fractional quantum Hall state, generally believed to be something called a paired composite fermion state, to some type of stripe phase, and then back to a composite fermion phase. Well, this is interesting. What struck me when I saw this data in the lab a couple of years ago, when my students showed this to me, I said, well, you obviously don't know what magnetic field you're at, because this is not the n=1 Landau level, I said to them in my wisdom. This must be the ground Landau level, because this just looks like the 2/3 state, and that looks like the 1/3 state. But of course, my students knew precisely what they were doing. This is indeed the n=1 Landau level. These filling factors are correct. It just looks like the ground Landau level. So by tilting the sample way out there and putting all this parallel field on, the system has somehow decided it wants to be, or it looks like it's in the ground Landau level. So let's talk about that for a minute. So Landau level mixing is something we think about a lot. Why do we think about it? Well, here's a cartoon of the fan diagram for the Landau levels. So I've ignored the spin splitting. At 5/2 filling, the Fermi level would be, say, here. If I now ask how big is the Coulomb energy on the scale of that cyclotron energy, well, it's a big number. It's kind of about that big. So it's clear that you should expect that due to Coulomb interactions between the particles, Landau levels are going to be mixed like crazy. So that's an important thing to think about. Now, there's also, and this is something which is generally ignored, not always, is that you have a quantum well with a certain confinement potential. And in that confinement potential, there are various quantized electric subbands. For example, there's the ground level, and then there's the first excited level. Each of those has a Landau fan. And generally, most often, we simply ignore the upper electric subband because it's so high in energy that no one cares about it. Okay, so all this Coulomb energy maybe doesn't really do much to couple in these states up here. But this sample, the one I'm showing you, isn't like that. It's like this. You can calculate in a simple way. You can use a self-consistent Schrodinger Poisson solver to figure out what the subband splitting is. And for the sample I've been showing you, which was a 400 angstrom wide quantum well, the alignment of the bands is really like this. So if you think about it for a minute, if you're at 5/2 filling and you look upward in energy because you want to mix, who's the nearest empty state? It's actually the lowest Landau level of the next subband. It's not the next Landau level of the same subband. So this has you can imagine, could have a profound influence on the way the Landau level mixing affects things. Okay, so furthermore, when one tilts the magnetic field and adds an in-plane component, that enhances the coupling, even at the single particle level, between Landau levels and different subbands. That's a simple result of quantum mechanics. So let's make an experiment then. If this has something to do with the physics, let's create a sample in which the subband alignment isn't like that. This is, the idea here is to make the same sample, except make the quantum well width narrower, and push those electric subbands up higher in energy, and hopefully keep everything else the same, the density of the electron gas, the mobility, and so forth. And fortunately, we were able to do just exactly that. These are precisely the same parameters that I gave you for the previous sample, only now the well width is 300 angstroms. This is the appropriate diagram. We've, again, calculated the energy splitting between these levels. It's about twice as big as it was in the 400 angstrom quantum well. So you think anything will be different here? This was the experiment we chose to do. Well, we did it. And it just worked exactly the way you might have guessed it would work. Here's the data I just showed you in the 400 angstrom quantum well. 5/2 state, anisotropic state, reentrant isotropic compressible state. Here's the sample that otherwise is the same except for the well width, as far as we know. 5/2 state, no 5/2 state, tremendous anisotropy. Keep tilting, the anisotropy just goes out of control. So it never returns to this lowest, to this compressible state, which looks like the lowest Landau level. So this is at least qualitatively consistent with what I'm trying to argue. Now, there's a further test that one can do. You could ask the question now, is it just the well width that matters? And my argument would be no, it's not the well width. It's actually the relative alignment of the different subbands. So let us take, again, a 300 angstrom quantum well, but let us double the electron density. If we double the electron density, the dot corresponding to 5/2 moves out to higher magnetic field, where once again, the nearest empty level is actually the lowest Landau level of the second subband. Same 300 angstrom width. You follow how I'm doing this sort of a triangle in Gedanken experiments. Well, they're Gedanken here, but they're not Gedanken here. So here we go again. Both of these samples are the 300 angstrom data that I'm telling you, 300 angstrom well width that I'm talking about. Here's the data that I just showed you for the low density sample, with the magnetic field at 5/2 being around 2.6 Tesla. But here's the higher density sample. Now 5/2 is up roughly twice as high in magnetic field, around 5 Tesla. It goes away and becomes anisotropic, and then boom, it comes back, and it's this isotropic compressible phase. So this probably isn't a proof, but it's a pretty strong argument that it's these relative alignment of these different energy levels that's important in determining what the fate will be of the 5/2 state as you tilt it. It illustrates once again that there's a complex interplay of different phases here that one has to contend with. So here's, I've already talked about this picture about quantum zoology and how the level, and I've just made the argument that the level alignment, not the level spacing itself, but the level alignment is what is the key. We don't know a whole lot about this reentrant isotropic compressible phase. It sure looks like the standard composite fermion liquid. It would be very nice to do some more sophisticated experiments. In particular, a good experiment to do would be to do surface acoustic waves in this highly tilted configuration and search for the anomaly in the conductivity, which was discovered long ago by Bob Willett at 1/2 filling of the lowest Landau level. That was a very strong signature of the composite Fermi C. We should try to do that experiment here again. We have not yet done that. Now, the last little topic, and I'm only going to say a word or two about this for single layer systems, is this. This is the same data that I've been showing you all along. And I mentioned at the beginning, as we tilt, the 5/2 state is destroyed, but in this sample, the 8/3 and the 7/3 stay nice and robust. And I don't have time to tell you about how their energy gap varies exactly as a function of the tilt angle, but you can see the states are there. There's no question about that. Well, let's focus on the 7/3 state just for a moment to see an interesting little fact. An interesting little observation. These are 3 different sets of data at different tilt angles. I'm plotting the resistivity, ρxx or rxx, measured in these 2 orthogonal directions, as I've talked about. When the sample is not tilted, they should be pretty much the same, and they kind of are. They're pretty close. It collapses to 0 at low temperatures because it's a quantum Hall state. However, as soon as I tilt it by even just 19 degrees, you get a lot of anisotropy that persists up to very high temperature. This is the striped phases or some type of broken symmetry state developing. At low enough temperature, fractional quantum Hall state takes over and causes the resistance to crash. A gap opens. However, at 44 degrees, you notice something strange. At high temperature, the anisotropy is bigger than ever, and as you go down in temperature, it looks like the gap is opening, and then all of a sudden the anisotropy turns on again. And in particular, there's a sharp upturn in the resistance. If I tilt it still further, we do this with a string, and every once in a while, if you pull it all the way to 75 degrees, the string actually breaks. But this time it didn't break, and you can see the anisotropy gets reduced again, reminding you of this coupling to the lowest Landau level, and the upturn becomes much smaller. If you focus in at 66, in this particular sample, at 66 degrees of tilt, this effect is very pronounced. Here at about 50 millikelvin, things just change. Turns around, starts to go up. So what the heck is going on here? Is it just giving up quantum Hall effect and becoming stripes? The answer is no. If you look at the Hall resistance, it develops a plateau on cooling between 200 and 100 millikelvin. At 50 millikelvin, it's still a Hall plateau. At 15 millikelvin, it's still a Hall plateau. So in this regime, at the very lowest temperature, where there's a 100-to-1 difference in the resistance measured in the two different directions, there's still a quantized Hall plateau. Now, this is very peculiar. This is something we've not seen before. We call this obviously an anisotropic fractional quantum Hall state. We don't really know whether it's homogeneous or whether it's some phase-separated mixture of stripes over here and liquid over there. We don't know the answer to this. Something that one needs to study further. There is theory out there. There's been actually since a long time ago, there was an idea from Bob Joint that, in fact, the one-third state even, he was studying the one-third state, in a tilted field might decide to acquire an anisotropy. He didn't go much further than suggesting this idea. There's a much more recent paper along the same lines, and frankly, I can't tell the difference between these two, although I'm sure there are important differences. To me, there aren't. That, in fact, there could be a pneumatic phase which has both an energy gap and yet strongly anisotropic transport of its charged quasiparticles. So this is an interesting frontier topic. Now, I want to switch gears. How much time do I have left?
Oh, yeah, 15 minutes.
15? Okay, that's plenty. Okay, that's plenty of time. All right, so I want to now talk to you about double-layer two-dimensional electron systems. This is, again, a fairly old topic. I'll start with some very old data. This is a picture from, I think, 1992 or 1993, I don't remember, in which I have a double quantum well grown by Lauren Pfeiffer to have about 1 million mobility in each of the individual layers, and they're pretty close together. I forget what this data is. It's probably about a 30 angstrom barrier. I don't recall. And we measure the Hall effect in this double-layer system. And we find there's a series, this is at high temperatures, about half a degree Kelvin. We find there's a series of Hall plateaus, one of which occurs at h over e squared, which sounds like the integer quantum Hall effect. And indeed it is, obviously an integer. However, this Hall resistance is measured for 2 layers in parallel. So really, this is a system in which the individual layers are at 1/2 filling. So this is surprising somewhat. The individual layers are at 1/2 filling, and we know from years of experiments that if we were to somehow pull those layers far apart but keep their density the same, this quantum Hall effect would have to disappear. Because then the 2 layers would be completely independent of one another. They'd both be at 1/2 filling. They would have composite Fermi liquids. There would certainly be no quantized Hall effect. So there is one here, and it has something to do with the proximity of the layers, the fact that they're close together. And let me just put it to you that since years of experiments, we know that this is not simply the effect of the tunneling of electrons between the 2 layers. It's in fact driven by the Coulomb interaction. There's some type of ground state here that's different than the ordinary ground states you find in a single layer system. So let me tell you in a very much a cartoon view what the charged quasiparticles are like. And why is the nu equal 1 state, this nu total equal 1, nu total being nu 1 plus nu 2, why is it so special? So here's a cartoon. And it's nothing more than a cartoon, so please don't take it too seriously. So here is a semiconductor. The way we learn about it in high school, it's got a valence band down here and a conduction band up here and an energy gap in between. As we know, if we make a superconductor, we have, again, an energy gap between quasiparticles and quasi-holes, but we have a Cooper pair condensate sort of at 0 energy. And that Cooper pair condensate is the thing that's responsible for superconductivity. It's what carries the current in a dissipationless manner through the sample. So the distinction between semiconductors and superconductors essentially comes down to the existence of this condensate, at least at this cartoon level. Well, it's sort of similar in what I'm telling you. In an ordinary quantum Hall state, ignoring the edge states, please. In an ordinary quantum Hall state, in the bulk of the sample, there's an energy gap between the charged, the charged quasi-holes and the charged quasi-electrons, and that has some magnitude, and we can measure that. We know it's there. That's what's responsible for the Hall plateau and the vanishing resistance. On the other hand, and here's the crucial point that you should, if you want to take away anything from this talk, you take away this, that at filling factor 1 in a double-layer system, there is not only that energy gap between the charged excitations, there's also a condensate that lies at zero energy. Very analogous to the Cooper pair condensate in a superconductor, with the important distinction that the Cooper pairs are neutral. They consist of electron-hole pairs. They are excitons. But other than that, pretty big difference. Other than that, this is very analogous to superconductivity. You're not going to carry much electricity with a neutral condensate, so there comes questions about how you can measure this thing, but this is what should be there. So we know this. We can make fancier pictures of it like these. I'm not going to talk about this. The basic idea is that any of you can realize that if you start with two half-filled lowest Landau levels in the two layer, one on each layer, a red one and a blue one, and you make a particle-hole transformation, you can talk yourself into thinking about electrons in one layer and holes in the other layer, and then a filled shell, just like you do in a semiconductor. It's no different than the way you talk about holes in the valence band. You carry around the filled valence band in your pocket. Here you have to just carry around the Landau level in your pocket. If you do that, you can sort of guess that maybe excitons form between the electrons and the holes in the two layers. Maybe they condense. It's all maybe. Maybe there's a wave function, which we know there is, that looks a lot like the BCS wave function for a superconductor. Almost identical. It has, importantly in it, a macroscopic quantum phase, just like in a superconductor. Gradients of that phase will correspond to currents in the condensate, or currents of those excitons that I've told you exist. How we measure them is another matter, but they ought to be there. This system then is kind of interesting. It has two ways to transport stuff. If you try to drive electrical currents through both layers in the same direction, which is what you would normally do by just putting contacts on the edges of the sample, that's not going to be carried by the condensate. Condensate's neutral. If the currents are going in the same direction, if anything, they want to tear apart the excitons because the excitons are plus and minus. So this degree of freedom is only carried, really, by the charged quasiparticles in the system. And they have interesting structure, which I won't talk about. On the other hand, you could imagine doing an experiment in which the electrical currents are flowing in opposite directions. If they're flowing in opposite directions, then perhaps the excitons could be responsible for carrying that. Because if they move uniformly in one direction, the positive's going one way, the negative's going in the same direction, so the currents are in opposition. So it might be possible, if you could do this experiment, that you could lay your hands on the excitonic degree of freedom, or the condensate degree of freedom. Okay, how do you want to do this? Well, it turns out the best way to do this, and this idea really came out of the Stuttgart group, I should point out, the best way to look for this, not the only way, but the best way, is to get rid of the charged degrees of freedom. Make them black, so that the excitons will sort of stand out in some way. How do you do that? You use a Corbino geometry. To my knowledge, this is maybe not the only good application of the Corbino geometry, but it's certainly one of the best. We know that if we make this geometry, quantum Hall systems are topological insulators. They have conducting states on the inner boundary and on the outer boundary. And if the quantum Hall state is well developed and we try to drive a current, put a voltage, say, between the inner and the outer boundary, no current's going to flow. Because the interior of every topological insulator is an insulator. So you can do this experiment. We do it all the time. And indeed, no current flows, or very little at low temperatures. Okay? So that's it. We're going to work with that to see if we can pick out the excitons. So here's a picture to best put you on the right page about how the drawings are going to look I'm about to show. When I show you this, it means two layers, contacts on the inner rim, contacts on the outer rim. There are no edge states connecting this contact and that contact. That's crucial. Okay, so we do the experiments. Here's the first experiment that we do, the ordinary one. We put the voltage in common on both edges, some battery. We ask how much current flows. We sweep the magnetic field. Every time a quantum Hall state develops, the current vanishes because the bulk is insulating, as you would expect. At nu total equal 1, which is this bilayer quantum Hall state, again, it doesn't vanish, but it becomes very, very small. If the sample were better and I was at lower temperatures, it would get smaller. So it's doing what it should do. The background, like the bulk, is opaque to charge transport. So let's do a different experiment now. Let's do this one, where I put the battery just between the contacts on the outside rim. This looks like a tunneling geometry. In fact, it is a tunneling geometry. Current might flow between the two layers due to tunneling. Well, for reasons that I'll explain in a second, I have set the experiment up in such a way that that tunneling is suppressed. So here's the current that flows as a function of the battery. There's not much going on, pretty much zero. Now, those of you that know something already about this subject are probably confused at this point, because one of the signatures of this phase actually happens to be that the system likes to tunnel like crazy. So here's another set of tunneling data, which I said, the red one is the one I just showed you. What in the world's going on here? The blue data is taken with the magnetic field perpendicular to the sample. And one of the beautiful properties of this phase is that it shows a tunneling anomaly which looks extremely like the DC-Josephson effect. There it is. It's beautiful. Lots of current, no voltage, right at zero bias. I wanted to destroy that for the purposes of this experiment, so I added an in-plane component of field. It destroys it in a way analogous, which I can talk to anyone about the details of this later, and in a way very analogous to the way an in-plane magnetic field on a Josephson junction suppresses the critical current, something called the Fraunhofer pattern. You put on enough magnetic field, it just wipes it out. It winds up the phase in a complicated way. Okay, so that's the beginning. I've done that. Let's just assume I've done that. Now, let me come along and do the following. The blue data, again, I already showed you. It's for this experiment. The red data, in which there's plenty of current flowing, I have put an electrical short circuit between the two contacts on the opposite edge. And now a lot of current is flowing. But I just got done telling you that the bulk is an insulator. So what's going on? There's two experiments that I'm showing you that look contradictory. The first experiment was this one. Into within quotation marks, I should have added, no current flows. But then I just wired up differently, and a lot of current flows. Now, how can this be? Obviously, if you were thinking about this the way everyone naturally would, as two independent layers, you would say this is not possible. If the two independent layers are both insulators, no current will flow in either case. If they were both conductors, current would flow in both cases. So that's not the right way to look at this. It has to be something about the fact that this is not two independent layers. And that's why this is a good experiment to do. It goes right to the heart of the matter. It looks at the system as a coherent bilayer. And you'll recall that I suggested to you that if excitons were present in the condensate, they could transport current in opposite directions, all by themselves, which is precisely what is needed to explain these things. Oppositely directed currents would not produce any current in this experiment, but it would in this. Now, how do I prove that this is what's actually happening? I have to go and measure the current over here. I can easily do that by setting up the experiment appropriately. I do that, and I find out that if I measure the current over here, and I measure the current that the battery actually is supplying, they're exactly equal. So the current must be traversing this otherwise insulating bulk by virtue of the fact that everywhere locally, the currents are in opposition. This is counterflow transport or exciton transport, overcoming the insulating character of the bulk. How does this happen? Well, here's a cartoon. This is an even worse cartoon than the previous one. Here are my two layers. Over here on the right, let's assume the layers are in the coherent phase, or in the excitonic phase, by some means. Whereas over here, they're independent. It's actually not so hard to produce this. And let's imagine that I send an electron in from the left in the red layer. If I do that, here it comes. This is the beauty of PowerPoint. It comes in nice and slowly, and then boom, it creates an exciton and travels off. So this should remind you of something called Andreev reflection in a superconductor. It's exactly what it is. with the difference being that the Cooper pairs here are neutral. So the retroreflected particle is not a hole, it's an electron again. Particle that goes in. In a superconductor, you send in an electron, you get back a hole, and you launch a Cooper pair. That's the only way you can conserve charge. Here, in order to conserve charge, you must retroreflect an electron. And furthermore, you must retroreflect it in the opposite layer. So what I've shown you is that this is possible. This is the experiment that I've just shown you. You can hook up a battery over here to a system that is otherwise insulating and deliver energy and warm up your resistor over here by virtue of these excitons traveling across the bulk. We had done experiments, we and other people had done experiments like this in Hall-bar geometries, where edge states were always connecting all of the different contacts. And it was not possible in those experiments to assert that there was anything going on in the bulk. Here, there's just no way out of it. It must be going through the bulk. But this suggests an alternative experiment, and I'm just about finished now. Why not this one? This should work too. Now I'm not even going to connect the layers at all together with any wires, but I'm going to suggest to you that the current still ought to flow because the same process is available. This looks like something called Coulomb drag, which many of us in this audience have played with over the years. What about this? Will this experiment work? And we've done that experiment, and you can set up the geometry. There it is. Only thing I'd like to point out in this picture is that I'm going to define the sign of the currents to both be positive if they follow the directions of these arrows. So they will both be positive if, in fact, in the bulk, they are in opposite directions. So we do that experiment, and we observe this. Blue and red correspond to the current in the drive. Blue is the current in the drive layer, I believe. And red is the produced current in the electrically isolated other layer. And if the drive is not too large, say below about 200 microvolts here, those two currents are just exactly equal. They have to be equal. If this system drives excitons, and only excitons, then obviously they're equal. Every electron has a hole attached to it. On the other hand, if somehow those currents aren't equal, then it must be true that a net current is flowing from one edge to the other, which apparently is what happens at larger drive levels. I don't have time to explain in this talk, but in fact, that's precisely what goes on here. As we increase the drive, in other words, put on a bigger battery, the insulating character of the bulk to charged excitations breaks down. And something we call sigma XX becomes finite at large drive levels. And in fact, we can simulate this data from the measured values of sigma XX measured independently. So I think this really kind of closes the loop on this. It proves, I think, that this exciton transport works, and that one manifestation of it is that it produces something we affectionately call perfect Coulomb drag. The currents in the drive and the drag layer are exactly equal, even though the layers aren't connected together at all by any wires. Okay, so I'm going to quit now. I'll just put up my conclusions and let you read them. I won't bother reciting them all. Thank you very much.
Thank you very much, Jim, for this fantastic overview about exciting physics in the two-dimensional systems. Other questions? Perhaps I can start. You spoke only as total filling factor 1, half and half, but you know, in unbalanced is always a total filling factor. Is 1/3 and 2/3? Is this an exciton transport or not?
Okay, so that was a good question. I couldn't have paid you to ask a better question. So what we know is that, first off, what Klaus said is exactly correct. That it turns out that it's not the 1/2 plus 1/2 that's important. It's that the sum of the two adds up to 1. So you can ask about imbalance situations like 60-40 or 2/3, 1/3. We know that for small amounts of imbalance, the system actually is more stable by going into the excitonic phase than it is when it's balanced. This is a small effect around zero imbalance. If you go all the way out to 1/3 and 2/3, it depends sensitively on how close the layers are together. If they're close enough, the excitons win. If they're farther apart, two independent fractional quantized Hall states develop. And we wrote a paper actually about 3 or 4 years ago showing one example of how that transition works. It seems to be a first-order phase transition.
So along the same lines, Along the same lines, have you looked at drag at other filling factors when the new total is not equal to 1, and whether one can learn something interesting about other fractional hot states?
The answer is no. We haven't had time to do that. It would be, if I sent an email to my students right now and asked them to do that, I think they would all quit. So this has been going on a long time. But it's a great idea, one that we would certainly want to do. I should say that we did examine years ago something called quantized Hall drag, which is a different type of measurement than this, done in a Hall bar geometry. And we found that that was very robust against charge density imbalance. But this experiment we've not done.
What is the critical temperature for exciton condensation? What defines this?
Are you asking about the temperature dependence? Was it the temperature dependence?
Yeah, what is the critical temperature for exciton condensation? What defines this critical?
Well, I don't know what defines it. I only know what I observe. So in the experiment, there's various things that you can look at. This effect, or you can look at this tunneling signature that in the perpendicular field, which is actually very sensitive. And what you find is that as a function of temperature, let's say the layer separation is some fixed value. As a function of temperature, there's a smooth turn-on of the strong tunneling anomaly. In fact, all of the features, I would say, that we observe turn on smoothly as a function of temperature. You need to be, in these samples, you need to be below about 0.5 Kelvin for this to be true. But there's no discontinuity in anything. There's no evidence of a really sharp transition. We think, although we don't really know for sure, that this transition is likely first order, but certainly smeared heavily by the disorder that's present in the samples.
What determines anisotropy between 0 and 1 minus?
What is the origin of this? So that's a $64,000 question. So we know a lot about that I didn't have time to talk about. So in the early days, every sample that we would look at always showed that the high resistance, this is out at 9/2 filling, where you don't need a tilted magnetic field to see the anisotropy. It was always the case that the high resistance direction was along the 1,1 bar O direction, not along 1,1O. We also found that if we applied a parallel magnetic field, depending on the orientation of that parallel magnetic field, we could rotate those directions of the anisotropy. So something in the sample, in the absence of the parallel field, must be breaking the symmetry of the crystal lattice. There are probably people in the audience here who will say, yes, I am sure of what it is. I'm not quite so sure. It's likely that this is a combination of piezoelectricity in gallium arsenide and the fact that there's a free surface that breaks the symmetry, which would otherwise be present if the system were a bulk gallium arsenide crystal. We're not sure about this, but it seems to be a plausible explanation for why this anisotropy exists.
Because we have the same problem in anisotropy on gallium manganese arsenide, that we have a uniaxial anisotropy, which we do not understand very well. And we believe now that it's formation of dimers, that if you have alloy like aluminum here, aluminium gallium arsenide, this aluminum not necessarily is randomly distributed, but grows along one direction. It's could be our interpretation of that.
Some over there.
Please.
Can you probe this excitonic condensate optically?
People have. Aaron Pinczuk, for example, and Vittorio Pellegrini in their group, they have done inelastic light scattering. I'm not an expert on this. I would suggest you ask them. But this system has definitely been examined through optical methods. Way up there.
There was one question here, please.
So what's the effect of disorders on the excitonic modes for bilayer system?
What's the effect of disorder?
Yes, right.
It spoils everything.
Yeah. I guess some disorder may cause.
Yeah, so this is this is another $64,000 question. I mean, if I understood the role of disorder and interaction simultaneously in this system, I guess I'd be famous. So I don't. What I know empirically, though, is that obviously if the sample is too heavily disordered, I mean really badly disordered, the effect simply doesn't exist. On the other hand, in these samples, which are not so clean, these are double layer samples, so they're not 30 million mobility like you can obtain in single layers. So they're not very clean. Several of the quantitative predictions of theory concerning the various things that I talked about here are not observed, are not well observed. So what do? We say, oh, it's disorder. Do we really understand the mechanism? Probably not. Exactly how that goes. People use phrases like unbound vortices at low temperatures. I don't have a microscope that shows me unbound vortices, but I know that the physics is not behaving in the sort of canonical way that we would expect for a Kosterlitz-Thales superfluid, of which this is supposed to be an example.
Okay.
We had already two $64,000 questions. Now, so $100,000. What's the best way to see AC Josephson effect? Or is it AC Josephson effect? Or is there no chance?
I know you're working on this, Klaus. You have to be. I think the best thing to do, and what we're trying to do is right now is to look for Shapiro steps. That would be one nice thing. Shine radiation in, and hopefully that's a lot easier than trying to get the radiation out. Shine radiation in and hope some beautiful steps show up. That experiment, even if it succeeds though, I don't think is going to be a killer because there will be photon-assisted sidebands to the tunneling too, which are distinct from the coherent Shapiro steps, and whether we'll be able to tell the difference between these two remains to be seen. If we put on a DC bias onto our tunnel junctions, in principle this thing is radiating. I can't imagine we'll ever detect that. But maybe there's some smart person out here who'll figure out how to do it. I would love to do that experiment.
Okay, thank you very much for this wonderful talk.